discussion, but we will start it as an information retrieval, what information retrieval is, and what are some of the issues involved. So what is information retrieval? It's nothing but a field of study dealing with representation, storage, organization, and of course, access to documents. And when we talk about documents, these documents could be books, could be reports, could be pictures, videos, web pages, or multimedia files. So document is a very general term in the context of information retrieval, and it might mean any of these things. The whole point of an IR system is to provide the users easy access to the documents that they might be looking for or they might be searching. And all of you have made use of or make use of information retrieval systems every day. For example, if you were to look at a physical system, our library is an information retrieval system. But on the computer, Google search engine or any other search engine is a good example of an information retrieval system where you go in, you type in some keywords or query, and the system returns you a list of web pages or links where you can go and get the information that you are looking for. So one can actually draw a simple diagram like this and say, all right, this is how an information retrieval system will look like. The user will have a query. The query will be used to generate some search criterion, and with that search criterion, the documents, a collection of documents will be retrieved. And in many systems, there is a possibility for relevance feedback. That is, when you work with Google, let us say you get the results. Some of the results may not be of your liking. Some of the results you might say, yeah, those are much more relevant. So there is an issue of relevancy of a returned document. So in some systems, when a user clicks on a document and tries to browse through it, the system will automatically capture that relevance information. In some systems, older systems, there might be an explicit way of getting that feedback whether the returned result was relevant or not. So relevancy does play a role, and the idea is that one can use that relevancy information to improve the search process, to improve the results for the user. All right. Now, one can make a distinction between what we call as information retrieval versus data retrieval. For example, you go to a database system and you give a query, and as a result of that query, you get certain data back. All right. Now, for information retrieval, you go to a system, you make a query, you get certain documents back. All right. So what's the difference? Are these two systems behaving identically, or are there some difference? That's what we are looking at. All right. So as far as IR systems are concerned, these systems deal with unstructured or semi-structured data. Remember, in the beginning, we talked about what we mean by structured data as well as unstructured or semi-structured data. All right. So information retrieval systems are able to handle unstructured, semi-structured data, while a typical database management system is built around structured data with well-defined semantics and well-defined meaning for different fields. So that's one big difference. Querying an IR system produces multiple results with ranking. Typically, that is what will happen. All right, you get lots of results, and those results are presented in certain order, rank order. All right. Partial match is also allowed. When you query a database management system, you will get exact or precise results or no result. That is, if your query does not match with anything that is stored there, you will not get any result. Otherwise, you will get exactly matching result with your query. All right, there's no question of getting multiple results with ranking and all. All right, so that's a difference. Here are some examples of IR systems. I already mentioned one, Google. This is an example of, I think, National Library of Medicine maintains a big database related to all the medical documents. So that's a huge library, and one can actually search for any medical related document or publication from that particular source. All right, so that's a nice example of IR system. PubMed is another one. That's another example. All right. Google, of course, we know is an example of IR system. All right. So we are all familiar. We have used such systems. All right. And let's look at what are the different types of documents. Although I already mentioned that, pictures, videos, images, those are all parts of documents. So let's look at them. All right. So text documents, that's typically what will be our first answer. That's what we mean by documents in IR systems, but also graphical and multimedia documents. There are some examples. Spoken documents, maybe voice messages, radio news, audios, podcasts. Those are all examples of documents that could be part of any information retrieval system. How do we characterize these documents? What kind of different characterization one can have? So one is what we call as a metadata characterization. This basically characterizes who owns the document. So who is the owner of the particular document? Who authored the document? When was it created? All that kind of information is what we call as the metadata characterization. All right. So it deals with all those issues, especially if somebody has an issue that, okay, somebody is plagiarizing my documents, then again, metadata is what will come into play. All right. Then one can talk about what is the presentation characterization of the document. So this refers to the attributes that control the formatting or presentation of a document. For example, you might be using different fonts, you might be using different inks, you might have a nice background in your document and all that. So these are all things that are made to look your document a little fancy or appear much more pretty. All right. So those are presentation characterizations. Then the third characterization is the content characterization. That is, this characterization refers to what is in the document. What is the content of the document? What is this document about? What is the topic that is being discussed in the document? All right. So this is the characterization that is of primary interest in information retrieval system. Because when you go and make a query, you're basically making query based on certain keywords, and you're looking for documents that have those keywords. Or through those keywords, you are defining what kind of content you are looking for in your document. All right. So that is what is important to us, and that is how we characterize documents in terms of information retrieval needs. Okay. So how do we represent documents based on their content in information retrieval? A common and easy approach is to represent documents by using a set of keywords or using a representation which is commonly known as bag of words representation. So what you do is you pick a set of keywords or indexing terms and you say that these keywords or indexing terms kind of give a reasonably good picture of what is in the document. So one can characterize documents through these keywords. At the same time, then one can actually search for documents using these keywords. So an indexing term in IR is a word or a phrase in a document whose semantics give an indication of the document's state. All right, so that's why we use them. And here is what we call as a bag of word representation. And this bag of word representation need not be limited to textual documents. That is, one can take this idea and apply it to even pictures or multimedia documents. For example, one could define certain basic building blocks of pictures, and one can say, all right, this collection of building blocks is present in this particular picture, and this another collection of building blocks is present in another picture. So that way one can again do a bag of words representation for pictures. Only thing is that in the case of textual documents, the words are already there, keywords are already there, all right? But in the case of pictures, if you want to use the bag of word representation, you have to figure out how to define those keywords, how to come up with those image patches which will serve as a function of word for bag of word representation. All right. Now, IR systems rely on indexes while searching for documents to satisfy a user's query. So basically, when you have a collection, that collection is used to create index. So every document in that collection has an index associated with it. And when the user goes and looks for a document, he or she gives a query that generates an index term, and then that index is used to do the search. All right. So that's how the search takes place. Now, there are different models for representing documents or doing searches. And one of the earlier model or the earliest model is what we call as a Boolean model of information retrieval. What is the Boolean model information retrieval? Basically, this model uses a set of keywords to define your entire collection. So suppose you have 100 documents, and then you pick, let's say, 10 keywords to define those 100 documents. Not all those 10 keywords will be present in every document. So what you can do is you can create a binary vector or a Boolean representation for each and every document. And in that Boolean representation, you have either 0 or 1. If there is a 1, that means the corresponding keyword or indexing term is present in the document. If it is 0, means the corresponding term is absent. All right, so that's a very simple scheme to represent documents. And to retrieve documents from an IR system using Boolean modeling, what one can do is one can construct a query of indexing terms. And that query, these indexing terms are linked by 3 operators: not, and, or are. These are all Boolean or logical operators that you use. And only those documents are retrieved that satisfy the query or give a Boolean answer of true for a given query. And this kind of method has been in commercial use for the last 3 to 4 decades. And many search systems still use the Boolean model. And here are some examples of those search systems. What one can do is, one can take this idea of Boolean modeling to create what we call as a term document matrix in a Boolean representation of documents. All right. So let us say that we have 1, 2, 3, 4, 5, 6 documents which are listed in blue here. These are nothing but, if you look at them, these are the dramas that Shakespeare wrote. So these are the titles of Shakespeare dramas. All right. If you go down in the first column, if you go down, Antony, Brutus, so on and so forth. Those are some of the characters that appear in Shakespearean dramas. All right. So what one can do is one can use those characters as keywords, let us say. And then each play can be characterized as a Boolean vector or a binary vector in terms of ones and zeros. So if you look at, for example, Julius Caesar play, basically the first 4 entries are ones and the bottom 3 entries are zeros, indicating that the first 4 characters, Antony, Brutus, Caesar, and Calpurnia, are part or present in that play, while the remaining 3 characters, Cleopatra, Mercy, and Wurzel, are not there. All right. So the idea is that one can generate a document matrix or term document matrix of this type and use that to do the query. So if I give a query Brutus and Caesar but not Calpurnia, so basically what we are doing is we are basically giving 3 keywords, but these keywords are being linked through logical operators. That is, we want Brutus and Caesar to be present in our document that we want to retrieve, but we do not want Calpurnia to be present in those documents. All right. So this query will be run against each representation, and wherever we get a result as 1, that particular play will be retrieved. And if we do not get any result equal to 1, then we will not retrieve any. All right. So this is how basically this kind of operation is performed. So these 0, 1 vectors for each term are known as incidence vectors. So to answer query, take the vectors for Brutus, Caesar, and Calpurnia. Calpurnia will be complemented because we said not Calpurnia. All right. And then we perform bitwise AND operation and see what we'll be getting. So basically that is the resulting query that we will be using. All right. And that gives us the way to search for the result. All right. So this is a pretty simple approach, can work nicely. But the problem is that this approach is good for understanding the model. But if you start thinking about your problem, you might be having millions of documents. So if you have 1 million documents, maybe you have 1,000 indexing terms. Then in that case, your term document matrix is going to be 1,000 by million. It will have 1,000 rows and million columns. All right. So that's a humongous matrix to maintain and search. Not only that, that matrix is going to be a sparse matrix. So sometimes what one can do is one can take advantage of that sparseness in the matrix. But in practice, the way implementation is carried out, it is not carried out along term document matrix, but it is carried out in a slightly different way. And that is what we are going to be looking at next. All right. But before that, let's look at what we call as ranking in Boolean model. So in the Boolean model, the documents are either relevant or non-relevant. There is no notion of partial match or ranking, because when you do a logical operation, answer is either true or false. There is nothing in between. All right. Now, sometimes what you like to do is, to a given query, instead of saying there is no document that matches, you might say, well, here are a couple of documents that do not match fully, but do match partially with your query. So in that case, what you may want to do is, you may want to implement some kind of ranking idea, which will rank your results, showing, okay, here are the documents that fully match, and here are the documents that partially match. Okay. So what one can do is, one can do a slight modification to the full Boolean search. And what we will do is, we can count how many query terms are there and how many of those terms we are able to match, and where the match is failing for how many terms. All right. So we can keep track of those numbers, and that can give us an idea of partial matching that we can use for a ranking. So here is an example. Let us say that we have 4 documents, D1 to D4, and there are 4 keywords or indexing terms, K1 to K4, and the term document matrix is as shown. All right. So suppose we give a query saying we look for documents that have K1 and K2 and K3. So in this case, if we look at document D1 and D2, D1 has all 3 of them. D2 also has all 3 of them. So we can say that there were 3 terms in the query, and documents D1 and D2 are both matching all those 3 terms. All right. So their score, you can say, is 3 each. If you look at document D4, D4 is not fully matching. It has 2 of the terms that we are specifying in the query. That means its match score is 2 out of 3. And D3 is matching only 1 of the terms. So its score is only 1 out of 3. So by doing this kind of trick, what one can do is, one can even use a Boolean model to produce ranked results and provide partial matching to the user whenever they need. All right. Okay. Now, in many cases, instead of using the Boolean operation to come out with true or false or how many terms are matching, it's very common to use some other functions for matching. And if you look at these functions, they should be familiar to you. Remember, we talked about Jacob's coefficient. We talked, I don't remember whether I mentioned dice coefficient or not, but we definitely talked about Jacob's coefficient. We definitely talked about cosine measure of similarity. All right. So basically, one can make use of any of these matching functions to define how well a pair of documents matches with each other. All right. So if you take any 2 documents and you figure out the keywords or indexing terms that are present in those documents, then you can see how many of those overlap with each other, how many are common, and how many are not common. Based on that, you can figure out what will be the matching score, and you could use for that any of the formula. All right. In practice, people tend to use Jaccard or cosine coefficients more frequently or more popularly. All right. Sometimes you want to give a specification where you say, well, I want this keyword to be present. I want this another keyword to be present, but I want both of these keywords to be present close to each other. That means they might be part of the same sentence, or they might be part of neighboring sentences. So you might specify that I'm looking for a document that has these keywords, and some of these keywords should be close to each other within a distance of 5 or 7 words. All right. So that is what we call as proximity searching in Boolean matching, or proximity operators in Boolean matching to do this search. All right. So instead of simply searching for the presence or absence of query words, we can specify an additional constraint that these words should be present in the neighborhood of each other or something like that. So here is an example query. What is the statutes of limitations in cases involving the Federal Tort Claims Act? And so that, and the query is specified in blue words. All right. So basically what we are saying here is we are saying, all right, these words should appear in the same sentence within 3 words of each other, and so on and so forth. So this kind of matching is very popular in certain domains. This example actually is taken from the Westlaw Library, which is the largest commercial paying subscribers legal search service. And it has tens of terabytes of data and about 700,000 users. Let's stop here. All right, I'm seeing some people are getting anxious. So we will stop here. That I have given you a brief introduction of information retrieval, but vector space model is the one that is currently in use. So, and that is the one we are going to be discussing in detail, as well as you will be doing some assignments using that model. So we will start discussing that model in the. You have vectors representing documents, and components of the vectors are non-binary components. Basically, that's what we have. So question is, how do we weigh terms? How do we find out what values should we be choosing for different terms so that we can represent a document vector? All right. These terms are, remember, nothing but the keywords or the words that we think are important in terms of representing the content of the document from a semantic perspective, what the document is talking about. All right. So obviously, one simple solution could be that one could say, all right, let's count how many times a particular word is present. And if a word is present multiple times, chances are that that word is more important for the document. Now, what happens is that if you take a look at 2 words, let us say one word is present 3 times, another word is present 5 times. It doesn't mean that the word that is present 5 times is 5 times more important compared to the word that is present 3 times, and that is only 3 times important. All right. So the point is that there is no linear relationship between the number of times a word is present and its importance. The relationship is more like a non-linear relationship. So typically what one can do is one can think of some kind of function which is a non-linear function of the frequency or how many times a word is present. So in this case, one can think of a log function, for example, 1 plus log x, where x represents how many times the word is present. Or it could be a square root of x, or one can think of any other nonlinear function. Now, this does help us, but it still doesn't capture the occurrence of a term in a document. How important is that? Because the importance of a term also depends how frequently it is present in other documents. Because we are looking at a collection of documents. We are not interested only in just a single document, but we are interested in a collection of documents. So if a word is present let's say, one time in every document. That means that word really doesn't tell us anything specific about a particular document because it's present all across. All right. On the other hand, if a word is present only in very few documents, that means that word does have something important because otherwise it won't be present in those few documents. All right. So we need to take care of two things. Number one, how many times a word is present in a document and how many times the word occurs in the entire collection of documents. By combining those two things, we can come up with some suitable weighting scheme. So the weighting scheme that is used in practice is called term frequency inverse document frequency scheme. And let us look at this scheme. So let us say that we define term frequency as a TF sub ij, which basically is telling us that how many times word wi is present in document dj. So we have a jth document and we are looking at the ith word and we count how many times that word is present there. And let that number be TFIJ. Similarly, let us use DFI as the document frequency, which tells us the number of documents in the collection that have the word WI. So that many documents in the collection have that particular word. And CFI is the collection frequency, that is the total occurrences of word WI in the entire collection of our documents. All right. So based on this, one can calculate what should be the weight value assigned to the ith word for document J. So if you look at the vector representation for document J and go to the ith component of that vector, that ith component will be referring to the ith term. So that term has a weight value that is given by this formula. So the formula is 1 plus log of TFIJ multiplied with log of n by DFI. And this is if the term frequency is greater or equal to 1. If that term is not present, obviously the weight for that document is 0. So if you look at the expression on the right-hand side, you have two components. There is a log component of term frequency, and there is a log component of the inverse document frequency. So that's why this scheme is known as TF-IDF weighting scheme or term frequency inverse document frequency scheme. All right. And you can see that the term weight increases with the number of occurrences within a document. And the term weight increases with the rarity of the term in the collection. So if a term is present fewer times in the entire collection, it is deemed more important. And obviously, if it is present multiple times in a document, it is deemed important. So that's how the weights are calculated. So here is an example just to give you an idea. So let us look at these 4 terms: car, auto, insurance, and best. And the document frequency for these terms are shown there. All right. And the total number of documents is given as shown, 806,791. All right. So based on that, one can calculate the log of inverse document frequency. That is what we are calculating above. And then once you look at the term frequencies for these 3 documents, for these 4 terms in 3 documents, document 1, 2, and 3, and let us say those are the numbers that are given to us, then what we can do is we can calculate the weights that will be assigned to these terms. So essentially for document number 1, the weight for car will be 4.06, and that calculation is shown in the slide. And similarly, you will get the weight for the remaining terms for document 1 as well as for document 2 and 3. All right. So basically what we have shown here, is how to get these term weights. So assume that we have done this calculation. Now you may want to ask, okay, how similar are document 1 and document 2? So what we can do is we can now calculate the cosine of document and document 2, document 1 and document 2. And that cosine calculation again is shown here step by step. And if you do the actual calculations, ultimately you end up with a number which is 0.623. So that is the level of similarity between document 1 and document 2. All right. So this should explain to you how the term weights are calculated and how one can then use those resulting vector representations to do the similarity. All right. The thing I haven't mentioned it, and we are going to look at, is how do we select these terms? Are there any steps to be followed? Anything to be considered for selecting these terms? So we'll come to that. So just to summarize what we have done so far, basically vector space model allows us to represent documents as vectors in a continuous space. And since we are representing now documents as continuous vectors, that means when we calculate the cosine similarity, it's not going to be false and true that we got in the Boolean model. Because in the Boolean model, we basically only got two answers. Either it was true or it was false. But now we have a range of similarity values in the interval of 0 to 1 that will be coming out as a result of measuring similarities between different pairs of documents. And since we have a range of values, what we can do is we can rank the documents in terms of their similarity. So given a query vector, we will rank the document at the top rank if that document has the highest similarity with the query vector. And then the next document which has the next highest similarity will be ranked number 2, and so on and so forth. So the main thing is that vector space model provides a convenient way of not only representing documents, but also ranking them in response to queries from the users. And generally, there are a fixed number of queries that are returned. For example, you can say, all right, I'm interested only in top K query, where K could be set to 10 or 20 or 100, whatever you. All right. Now, one might ask, okay, so we have a collection, we gave a query, and we got certain number of documents that came out as a result of our query. All right. Now, as you have experience with Google search or any other search that you might have used, everything that comes out as a result of your query is not necessarily relevant, not necessarily what you were looking for. All right. So basically what people do is people define two terms or two characteristics of any information retrieval process. One is we call as precision, and precision means the fraction of retrieved documents that are deemed to be relevant. So suppose you retrieve 10 documents, and while going through those 10 documents, you find that 8 of them are really relevant. That means 8 out of 10 are found to be relevant. So your precision will be 80% or 0.8. Recall is a fraction of relevant documents in the collection that are retrieved. So let's take the same example. So you retrieve 10 documents, 8 are found relevant. Now, if somebody allows you to browse through all the documents in the collection, and while browsing through, you find that there are 8 other documents in the collection that could have been retrieved. That means your system retrieved only 8 out of so many relevant documents. So that becomes the recall, that it was able to recall only X percentage of documents from the system. All right. So these two measures are commonly used not only for information retrieval, but a lot of times people also use them for displaying how good is a classification model. Okay. Now, another thing about precision and recall is that their values will change if you change the number of documents that you retrieve. For example, if you retrieve 10 documents, then you will get certain precision and certain recall. If you retrieve 20 documents, then your precision and recall will change. All right. So typically when people describe precision and recall, especially in the context of information retrieval, they basically tell you that we are calculating this for top K documents, where K is specified as 10 or 20 or whatever it is. All right. Now, sometimes people don't want to use both precision and recall as two measures. Rather, they would like to put them together in a single attribute or in a single metric. So there is a measure called F measure, which basically combines precision and recall into a single number. And the formula for F is as shown. And basically, the formula involves both precision and recall. And it also involves another parameter, which we call as alpha, which is how much weight you want to give to precision and how much weight you want to give to recall. Because in some applications, you may want to have more precision. In some applications, you may want to have more recall. All right. So basically, you can weigh the two by using this coefficient alpha. And alpha equal to 0.5 basically gives equal importance to precision and recall. And that is typically what is used in practice if you don't have any other specific needs. And for alpha equal to 5, F is given as 2 times PR divided by P plus R. And this measure is typically known as the harmonic mean, because F is nothing but a harmonic mean of P and R. All right. So now let's look at sorry, how the indexing terms are selected, or how does one go about selecting the indexing terms. All right. So we'll start with looking at an English novel called Tom Sawyer. And over here in this slide, I'm showing you in table 1 the common words that are present in Tom Sawyer. All right. So the word that is most frequently present is the, and that should not be a surprise to us, because this is a word which is used from a grammatical perspective, and it appears almost in every sentence. All right. So that occurs 3,332 times. And if you look at the other words that are present in this table, again, you can see that these words really do not carry any meaning. They are basically there to take care of grammatical rules, to put together different join together words or take care of pronouns and things like that. All right. So these are the words that are really not important. So the total number of words in Tom Sawyer is 71,370. And if you look at the number of different words, that number is about 8,000. All right. So you expect, okay, the total count is 71, 72,000, and different words are about 8,000. So a word on an average should be occurring about 9 times. Obviously, that is not true, because as we see, there are words that occur thousands of times, and there are words that might occur 9 times or even fewer than 9 times. All right. So obviously, one thing is clear, that the words that are kind of shown in this table are not the words that one should be using for indexing. All right. These words should be ignored. They should not be used. So now if we start looking at word frequencies and frequency of frequencies, all right? So that means how many times a word is present, all right? So obviously the words that are present many, many times, as we saw in table 1, those words are really not important. But the words that are present fewer times are the words that are important. So if you look at this table here, you will find that the words that are highlighted with blue arrow appear to be the important words, and the words that are characterized by the red arrow appear to be the words that should be ignored. All right. So there is an interesting law I just wanted to mention here, and this is known as the Gibbs law. And this law says that there is an inverse relation between the frequency of a word and its rank. Rank in some sense tells us, okay, you know, whether it is important and how you will, you know, take care of that word. All right. So in this case, the rank is being shown here, and we are showing you the frequency also. All right. So if you take the product of the rank and the frequency, for example, take the first word in the table, the frequency is 3332, and it's ranked 1 because it has the highest frequency. All right. So that product between the rank and the frequency is about 3332. All right. And let's do the similar calculation for the rest of the present. So the Gibbs law says that this relationship, frequency of a word and its rank, there's an inverse relationship between them. And if you multiply them, you should be ending up with some kind of constant. All right. So basically, that is what is shown also in this graph. And if one does the plot for rank frequency, that plot, if you do it on a log scale, will come out to be a linear plot. Why I mentioned Gibbs law? The reason I mentioned Gibbs law here is because Gibbs law is found in many areas. This is an example of a law which is known as the power law. Okay. Now, just to give you an idea, people, if you look at social media postings or the Twitter habits of different users, you will find that there are users who post tweets very frequently. Frequency of their tweets is going to be really, really very high. And there are users that post tweets very rarely. All right. So again, if you were to calculate the tweet frequencies and rankings, you will find that, again, tweet frequencies and ranking, that follows the Gibbs law. Same thing if you look at the items being sold on Amazon. You look at how many units of a particular item are being sold. So that will be the frequency, and then you rank them. Again, you will find that that relationship is going to fall into Gibbs law. So basically, Gibbs law says that many of these things, social interactions, purchases on the Amazon and all that, those follow Gibbs law. That means if you were in the market, or if you are trying to come up with a product, you have a choice where you could come up with a product that caters to the people that fall in the red area in this graph, or a product similar to the products falling in the red area in the graph. Or you could be having a product that falls somewhere on the long tail. All right. What does that mean? That means the products that fall on the long tail are possibly niche products. Those are products that appeal to a small population, while the products that fall in the red area are the ones that are going to be appealing to a large number of people in the population. So obviously, if you want to go for a niche product, you can possibly charge them more because there are a specialized product. So the idea is that Gibbs law does play an important role in terms of figuring out how you want to place your product or what part of the market you want to operate upon. And the same idea applies here in terms of the indexing term selection, how we want to select. So we don't want to select indexing terms from the red part of their rankings, but we want to select them from the long tail. All right, so I just wanted to mention that. All right. As we saw, the words that are most frequently present are of no use. So those words are what we call them as stop words. They are not content words. They are designated as stop words. And we basically want to filter them out when we want to build the document representation. Sometimes people like to perform an operation called stemming. Stemming refers to the idea of going at the root of a word. For example, you take words like compression, compressed, and compressing. These three words basically are conveying the same concept, all right? Except that the tense is different, but otherwise they are conveying the same concept. So what one can do is one can apply some kind of stemming algorithm to reduce these words to their common root, and then use the root word as the indexing term. All right. So if you want to read about stemming, there is a link shown here, and Porter stemmer is the most popular stemming algorithm. So you can read about it here. This used to be an important consideration way back when memory was expensive and computation was not that fast. Nowadays, given the memory is so cheap and compute power is so freely available and so cheap and so good, people really don't bother much about it. All right, so I thought I'll mention this here. Before you do the weight calculation, there is another operation that typically is done, which is called case folding. So what does the case folding do? It basically reduces everything into lowercase letters. So that way, you know, whether a word is written in all capital or it starts with a capital letter or it is all lowercase, they're all treated as same. All right, so that's an important step. Sometimes indexing terms are not single words, but they are phrases, because there are certain phrases made up of 2 or 3 words that do convey certain meaning. And what you may want to do is to use those phrases as indexing terms. So here are some examples of phrases: disk drive, below the belt, weapons of mass destruction. So instead of using weapons separately, mass separately, and destruction separately, weapons of mass destruction conveys much more meaning, and you would be, advised to use that phrase as your indexing term. All right. So there are resources available which tell you what are the commonly used phrases, and one can actually use them while building the indexing terms. All right. If you want to find phrases on your own, again, you can actually make use of parts of speech class, that is, characterize each word as belonging to a particular category of parts of speech, and then look for certain combinations like noun, noun, or adjective, noun, because those are the combinations that are found as useful phrases. All right. So you can do that. Term normalization is another step that you might need when you are doing indexing. What does this mean? It basically means that, people use number of different words for the same concept. For example, we could be using automobile, we could be using car, we could be using term vehicle. They all mean the same thing. Okay, so what one can do is one can basically perform what we call as the term normalization operation and say, all right, I will remove or replace every occurrences of car, vehicle, automobile, or anything else with one common term. Let's call it as a car or an auto. So that way you don't make a distinction when you are indexing between car and auto and so on and so forth. Okay. So basically, this slide shows you steps towards what happened. Let's pull it down. The remote control somewhere. All right. So this slide shows you what are the steps involved in doing the indexing. All right. So we start with, let us say, as an example, with a sentence which is called, it's a sad and beautiful word. All right. So we do the lexical analysis. So basically, we typically isolate all the words and then identify what are the stop words that are present, and we remove them. So we remove the stop words. After that, we are left only with 3 words from the sentence: sad, beautiful, and word. All right. And then if you wanted to do stemming, we will do the stemming. All right. So in this case, we do stemming. So sad remains sad, beautiful reduces to beauty, and word remains word. All right. And then we perform phrase extraction. All right. So in this case, sad does not form any part of any phrase, but beautiful word is a commonly used phrase. So basically, we can say, all right, beauty word basically is a phrase. All right. So basically, you can say that we got, okay. Then what we can do is we can now perform term normalization. So instead of sad, we have decided to use unhappy as a representative word. All right. So basically, sad is replaced with unhappy. And instead of beauty, the choice is pretty. So basically, that is replaced with pretty. So basically, we are left with now 2 indexing terms. The first one is unhappy, and second one is a phrase, pretty word. All right. So what we can do is we can basically create weights for them following the procedure that I have defined earlier. All right. So that's how typically you will go through a process of building a vector representation for a given document. Now, some of you might be beginning to worry that looks pretty complicated process, a lot of stuff involved. Yes, sure, it is complicated, a lot of steps are involved, but sklearn library does provide you with the tools, which when I show you the examples, you will see that using those tools, generating the document representation is pretty straightforward. All right, so we will come to that in a little while. All right. Yes, please.
I don't understand why in the normalization we have unhappy and pretty written with an I, not with an Y. Why they have written wrong?
I have to come closer to. Yes, can you repeat your question, please?
Okay. My question is in the normalization, why unhappy and pretty are written with an I, not like unhappy with an Y. Like the,
Oh, okay. Those are the rules to stemming. You know, these words that we have in languages, these words, if you start tracing back their history, so they originate from a root word, and from that word, there are a number of different versions of that word for different purposes. All right. So, yeah, normally we'll write unhappy with a Y, you are right. But this is the root word through stemming that you get. All right. Same thing for the pretty. All right. As I said, nowadays, not many people go and do stemming. So, but I just wanted to illustrate it here so that you know that it can be done, and if we need it, this is how it will be there. All right. Okay. So let's take a look at bigger collection and a couple of issues involved with the bigger collection, and then we will look at some examples of document representation. All right. So if you look at bigger collection, which is a more realistic setting, so it's not very surprising that you might be dealing with million documents. It could be, short memos in a corporation that over the years that have been collected, all right, or some long emails that have been collected, all right. So let us say that there are about 1 million documents, and each has about 1,000 words, all right. So if you take average 6 bytes per words, including spaces, punctuations, that basically is 6 gigabytes of data in documents. And while going through these documents, let us say that there are 500,000 distinct terms that you find, all right? Just for the argument's sake, that many distinct words or terms are there. So in that case, if you were to follow the document matrix representation, which I mentioned earlier in the last lecture, that's not going to be a very good representation, because with that representation, you will end up with a 500K times 1 million size matrix, all right? And that matrix is going to have 500 billion zeros and ones, because it's going to be a very sparse matrix, all right? So term document matrix representation is really not good for real world problems. It is good for smaller problems. It is good as a concept to look at different things, but not a good way to implement things. So in practice, you implement this idea of term document matrix, or the information that you need to store to figure out how we will calculate the term weight. Because in order to calculate the term weights, you need to find out how many times a term is present in a document and how many times it is present in different documents, all right? So those things have to be calculated. That means one needs to keep track of all that information. And that is done in a convenient way using the idea of inverted file structure or inverted index. And many of you, or maybe all of you, have gone through this data structure in your data structure class or in your analysis algorithm. So very briefly, I will just look at it. All right. So basically what we do in this inverted index scheme is that for each term, we store a list of all documents that contain the term T. And these documents are identified by their corresponding document ID. So every document is assigned an ID, you can say, all right, as a number, all right. So there is a document ID, which is a serial number, and basically we have a list of all the documents that contain the term, all right. And this information is saved or stored in the form of a linked list structure. So basically, the picture here shows you the linked list structure. So if you look at the term Brutus, basically it is present in document 2, document 4, document 8, so on and so forth. And similarly, if you look at the other two terms, the corresponding linked list is shown there. All right. The advantage of linked list structure is that it allows you to do dynamic space allocation, and insertion of terms into documents is easy. And this list is known as the posting list, and a particular posting is known as simply posting. All right. So linked list structure has posting lists, it has postings, and the terms or the indexing terms that you have, they define what we call as a dictionary. So you have a dictionary, and corresponding to every term in the dictionary, you have a corresponding linked list consisting of different postings, and each posting tells you the document ID where that particular term is present. So if you want to see how this structure is created, let us see here. Let's look at two documents. So document 1 consists of a statement: I did enact Julius Caesar, I was killed, I, the capital, Brutus killed me. And similarly, the document 2 is shown there, consisting of a couple of words. All right. So what we will do is, we'll basically, as the first step, do the lexical scan and isolate each and every word in the list. All right. So basically, we create a table, you can say. The first column in the table is the words or the terms as we come across them while scanning these documents. And the second column indicates the document ID. Since we have only two documents, so the IDs are only 1 and 2. All right. So basically, this table is created. Next step is we sort these terms in the table in an alphabetical fashion so that we have a sorted list of terms, or our dictionary is sorted in an alphabetical order. So we do the sorting. So basically, if you look at the table in the middle, you can see that we have sorted the terms, and the second column has the document number. All right. Now, what we can do is we can add another column where we count what is the frequency of that term in the given document. All right. So if you look at the final table here, we have three things. First column is the terms in the dictionary. Second column is the number, document ID. And third one is the frequency. All right. And once you have this, what we can do is now we can take this information and convert it into the form of a posting file, or convert it into a linked list and create the posting files. So that is how we will take from this center table and convert it into a posting file. And once the posting file has been created, then we can use those posting files to do the query processing. For example, if you were to give a query that retrieve me all the documents that have Brutus and Caesar, what we will do is we will locate Brutus in the dictionary and go and retrieve the corresponding postings. Next, we will locate Caesar in the dictionary and retrieve the corresponding postings. And then merge the two postings, because that is what is the list of documents where that query is satisfied. All right. Now, I think in your slides, you will possibly be seeing something here, which is being shown as dashed lines. All right. What you should be seeing in the slides that are posted on the Moodle, not the ones that you are looking right now if you are looking through the Zoom. But if you go to the posted slides in the Moodle, you will find that you have two linked lists there. And basically, the bullet points that I mentioned above, those corresponding results are shown there, and you see the result. All right. The reason you are seeing the dotted lines here is because I have shut off the animation. Otherwise, this would have come out as part of the animation. All right. So check it out there. All right. And if the list lengths are X and Y, then merging takes up the order of X plus Y. So it's a linear operation. All right. Another point I want to mention here before we move on is the query optimization. That is, if you look at the previous slide, I said, all right, first check Brutus, then check the second one, and so on and so. All right. Now, typically what happens is that corresponding to different terms, the size of the posting files will be different. Some terms will have a smaller posting file, some terms will have a larger posting file. All right. So it turns out that if you process the terms for query processing based on their size of the postings, then you can get some speed up advantage. So basically, that is what is done as part of query optimization. So basically, we process with the smallest posting file and move to the next smallest and so on and so forth. All right. And that is the reason we keep document frequencies in the dictionary. So if you are keeping the document frequencies in the dictionary, then that allows you to do this query optimization or do the implementation of the query in a more efficient fashion. All right. So there are a couple of points involved in terms of building an actual inverted file system and then doing the querying, etc. So some of them are mentioned here. In general, there are more ways of doing optimization. So we get document frequencies for all the terms, estimate the size of each R by the sum of its document frequencies. That gives you some kind of conservative estimate, and there are ways of doing that, and then process in increasing order of odd sizes and all that. All right. And some other improvement that one can make in the inverted list are use of skip pointers, dictionary compression, posting file compression, and so on and so forth. Now, if you are interested in reading in detail about some of these topics, please go to the course handout, and I think there I have given you a link to a book on information retrieval. And if you go and look into that book, you will find that many of these points are discussed in a lot of details. So I will highly recommend that you read that particular chapter where they talk about inverted list and query optimization and what are the different things that can be done. All right. So with this description, let's look ahead what we are going to be doing with in terms of the text and all that. So obviously, we will be coming back and looking at some point about document clustering. So because once you know how to represent documents as vectors, we can do clustering. So we'll be doing document clustering to organize a given collection of documents. We could perform document classification. For example, you might have a profile on some service where they send you the news stories that are of interest to you. So when a new story comes up, they need to know whether that news story is of interest to you or not. That means that news story needs to be classified into a category that is of interest to you. So obviously, there is a need for text classification or document classification. So basically, we'll look at that. Similarity search, we mentioned use of cosine similarity, but how do we do similarity search at a large scale? Little bit of search engines and link analysis. How does Google work? What is underlying techniques? Little bit of that idea. Sometimes you will find that simple use of indexing terms as we are discussing is not enough. Then there is a technique called latent semantic indexing or embedded word representation of documents and all that. So we'll look at some of those things. And also we'll talk about recommendation systems. How do we recommend you? For example, Netflix, how does Netflix recommend you films based on your previous history as well as based on your profile? So some of those topics we'll be considering in future. All right. What we like to do is to go over a small example of text processing using sklearn library. All right. And what I'm going to do is I'm actually going to skip through all this. You can actually look at them. I want to mention two things and then I'll show you another more detailed example. All right. So far, I mentioned that we are picking indexing terms, which are basically single words, or once in a while, there might be phrases. All right. Sometimes people like to pick what we call as n-gram word features. That is, instead of representing a document as a vector where each component of the vector represents a word, sometimes people find it more useful if each component of the vector represents an n-gram. What is an n-gram? For example, if you look at two words that are next to each other, then you say that that pair of words forms bigram. If you look at three words, then it is an trigram. So if you look at n words together means they are neighbor of each other in a sentence. All right. Then that forms an n-gram. All right. So you might, say, well, what is the advantage of bigram or trigram or n-gram over using 1 gram, just a single word? If you look at a single word, basically you're looking at a word in isolation. You are not looking at any context around it. And many times you know that even when you are hearing something or when you are reading something, even if you skip one or two words, or if you don't even hear one or two words clearly, you can still get the entire meaning of what is being said by the context. So the idea of using context is important because it brings you more information. So that's why people like to use n-grams. Obviously, nothing comes free. So when you use n-grams, there are some disadvantages. Okay. So basically, we will look at some examples and you will find that, bigram or trigram models are pretty useful to build the representation. All right. And we will make use of sklearn library. And there is an object in the sklearn library called count vectorizer. So that allows us to build document representations using 1 grams, 2 grams, 3 grams, and so on and so forth. All right. N-gram representation does increase the document vector size. So that is the downside. All right. So we'll look at some examples. Other thing we want to look at, and I'm briefly mentioning here, and then we'll come to an example there where you can read in more detail and see things in more detail. There are two issues with the representation of documents that we have discussed so far, which is using words and then assigning words TF, IDF weights. All right. So this is generally called TF, IDF representation or bag of words representation. All right. What are some of the issues here? Number one, the vocabulary size can grow so much because if you are talking of millions and millions of documents, then obviously the number of different terms that you're going to be coming across is going to be humongous. So the dictionary size can become so big that it may not fit in the memory for a very large corpus. So in that case, we will need to have multiple passes over the data to build the representation. And that obviously creates issues, or you can go for some parallel or distributed processing, but again, that creates its own issues. So sometimes what people will like to do is to make use of a vector representation that is of fixed size, irrespective of what is the size of your corpus or how many documents you're going to be dealing with. All right, that's number. Number two, the text classifiers that are typically built using TF, IDF representation. For example, all of you are familiar with, I think, spamming. You know, in your email system, you have a spam folder. That spam folder is actually nothing but a text classifier. What your system or email system does is that when an email comes in, it is fed to the text classifier. And that text classifier will decide whether that email is a spam email or it's a non-spam email. So one way these text classifiers work is that they look for, obviously, the words that are present in the email and then build a representation based on those words. Now, if there are words in the email that are not present in your dictionary, because the classifier has been built, so it's already there and it has its own dictionary. So if the word is not present in the dictionary, what the classifier does is that it basically discards that word. All right. That means that word is not used while doing classification for being a spam or not a spam. So if you discard all the words that are not in the vocabulary and just perform classification based on the words that are in the vocabulary, the system thinks it's not a spam email. And what spammers do is they know that this is how the classifier works. So they will put in regular words, but at the same time, they will throw in misspelled irregular words that will try to attract your attention. That's why if you look at some of the spam emails, especially the older ones, now I think there's a cat and mouse game going on, so spammers are coming up with new techniques and email classifiers are updating there. So what I'm telling you is, a little bit old scenario. And if you think of old scenarios, you would have found lots of emails with a lot of misspelled words and things like that. That was the reason they were misspelling them, so that they could clear through the spam filter. All right. So basically, in order to take care of these issues, there is a technique called hashing. And basically, hashing is used to figure out the weight values that are assigned to different indexing terms. And hashing results in a fixed size vector. So there is no issue of your vocabulary size increasing as you change or grow the corpus. All right. So with that, let's go to an example that I will go over. So let's, I think, let's check with these people. Can you guys see this? Anybody looking at the Zoom, can you see the new screen through the Zoom?
No, I can't.
You can't see this from data to decisions?
No, I'm still seeing the slideshow.
Oh, okay. All right. We'll remove. Yeah, we will change that. All right. And share screen. And okay. So you should be able to see this new screen, numeric representation of text, count vectorizer to hashing vectorizer. All right. So let's look at this. This is the blog post that I wrote, I think, a couple of years ago. Yeah, in 2019, while doing this course. All right. So basically, the first paragraph is just we have been talking about bag of word representation. All right. So let's look at an example of how sklearn library allows you to generate representations for documents. All right. So in this case, we will work with a very short corpus just for illustration purposes. So the corpus has 4 sentences, which are shown here. The sky is blue and beautiful and so on and so forth. All right. So there is an object in sklearn library called count vectorizer. And this can be used to convert text to a vector representation. Because in order to do anything with text documents, you need to convert them into vector representation so that you can apply clustering, classification, recommendation, whatever you want to do. So that is really a first step. All right. So let us see how you will do that, count vectorizer. So count vectorizer basically will count how many times a particular word is present in a given document, and it will also count the words presence over different documents, and then generate some kind of a representation. All right. So if you look at the code here from sklearn library feature extraction.txt, we import the count vectorizer. And then basically we create its instance as a vectorizer. And then we will fit this vectorizer to our corpus. And then basically get the result after the fitting. All right. So basically those are the steps that are involved. So that is what we are doing here. So if you look at the document matrix, before that, let me go over here and see what we are doing here is. So basically, okay. So we are getting the terms, we are getting their count values, and then we are pushing them into a data frame for later use. And we are then printing a document term matrix, which is saved in a data frame. And you can see here, what we are showing in this matrix here is there are 4 documents. So you have 4 rows, 0, 1, 2, 3, that correspond to those 4 sentences. And then the columns correspond to the terms that have been identified or isolated. And in this case, since we are not doing any stop words so far, so basically all the words that are present are here. And the matrix is showing the count values, how many times a particular word is present. So if you look at, for example, the first word and is present in first sentence or sentence number 0. It is present in second sentence. It is not present in the third sentence, and it is present in the fourth sentence. All right, so that's what we are. All right. Now, let us say that we want to apply stop word filtering. All right. So what we will do is we'll say, all right, let's see, is that what we are doing here? No, okay. Okay, so yeah, so we are saying here stop words equal to English. So basically we are telling the vectorizer that we don't want to use the stop words. And in sklearn library, they have a stop word from other languages also, okay? Because people could be using it for processing some other languages. All right, so in this case, we are saying, let's take a look at the stop word from English and let's use those stop words and filter them out from our corpus. All right. So once you do that, you will find that we are seeing here a new term document matrix, which does not have any of those stop words in it now. So basically, we have only 7 words that are present here. All right. And it basically gives you a count. All right. As I said earlier, the count is not a good way of representing things. What we like to do is to do the representation using term frequency, inverse document frequency. But before we do that, let's look at the n-gram word feature that I mentioned just a while ago. So what you can do is you can specify to this count vectorizer what kind of n-gram feature or n-gram range you want to use. All right. So the way I have specified n-gram range equal to within quote within parentheses 1, 2, it is telling that I want to use 2 consecutive words or 2 successive words along with each single word as features for the representing word representation. So a single word will be a feature as well as the single word paired with the next word will be a feature. All right. So that is what we are telling. And you can do this specification. If you look into the sklearn library, they'll tell you what are the different possibilities that you can have here. Okay. So in this case, if we specify, so you can see now the list of features or list of terms. So you have beautiful, beautiful blue is the second one, beautiful queen is the third one, blue is the next one, blue beautiful is the next one, and so on and so forth. All right. So basically you are now using 2 grams. And now if you look at the term document matrix, the number of rows is still the same, but look at the number of columns. We have now many more columns. All right. So that is what happens when you use the n-gram feature. The n-gram feature will increase the size of the vector representation. Okay. And in certain situations, that may not be desirable because that might impose additional requirements on your system. But in some cases, you might need to use it to get better results or better focus on the documents. So it's always a question of compromising between the different possibilities. All right. Now, our interest is in getting the term weights. All right. So what sklearn library does is that it provides you an additional vectorizer, which is called TF-IDF vectorizer. And as the name implies, this vectorizer directly gives you the term weights. The previous vectorizer, simple vectorizer, just gave you the counts. This one will give you the actual term weights. So let's look at this term vectorizer. And the weighting scheme is the same that we have discussed earlier. All right. So it is just repeated here for continuity's sake. So basically, that's the weighting scheme. So let's look at this vectorizer and run the same corpus with the stop words and see what results we get. All right. And we are still using n-gram equal to 2. All right. So with that, you can see here the term document matrix now has numbers like 0.28, 0.42, 0.53, and so on and so forth. All right. So basically, every element of the vector has either a value which is 0 or a value which is non-zero. All right. Some continuous number or some real number. All right. So basically what one can do is one can combine counting, term weighting in a single operation. And basically we can do that here. And that is what I'm showing you here. All right. So basically you have vectorizer. You can do the vectorization and then you can call TF-IDF vectorizer just to generate the term weights. Or you can actually use this TF-IDF vectorizer where you not only do the counting, but also generate the weights. All right. So that's what you will get. Now let's come to the hashing vectorizer. So as I said, sometimes you want to do the hashing. The reasons I explained to you why you want to do the hashing. So what does the hashing vectorizer do? Basically, I'm assuming all of you are familiar with the hashing operation, all right? So what you do is you take a string and you have a hash function and use that hash function to map that string to a number. And that number defines a location in a table, which is known as the hashing table, all right? So basically, that's what the hashing does, all right? Now, in the case of sklearn library, they use a particular hashing function because when you are looking at hashing, you have certain requirements from these hashing functions. One obvious requirement is, the avoidance of collision or at least minimizing the number of collisions that can happen. Another one is what will be the size of the resulting hash table and so on and so forth. And there are a number of properties. So based on some of those requirements, there is a particular hashing function that is used in the sklearn library. This is known as murmur3. You can do a Google search and learn about details of this function. All right. By default, this function uses a hash table of this size 2 to the power 20. So that's a pretty large size of the table. All right. That means every document is represented as a vector of the size 2 to the power 20. All right. Now, this hashing function returns both positive and negative values. All right. So basically, when you look at the entries in the hash table, you might see positive numbers or you might see negative numbers. All right. So the same corpus, if I apply the hashing and try to generate the result, this is the term document matrix that I get. In this case, I'm using a hash table of size 5, just to show that I had 7 terms without, after doing the stop filtering, if I'm using only 1 gram. All right, if you're using only 1 gram, you have 7 terms. And if you have a hash table of size 5, obviously there is going to be collisions. All right. So if you look at the entries here, anything which is non-1, so basically you see there are collisions taking place under column 5 at -2 or -3. So what happens in the sklearn implementation is that if a term gets mapped to a location where already another term has gotten mapped, then you increase the number or the value in that location. So if the location had -1 and you get another term mapped there, then -1 becomes -2. or it becomes -3. All right. So that's why you're seeing -3 as under column 5, telling us that there are 3 entries that are getting mapped into the same location. All right. This was expected because the hash table size is 5 and we have 7 terms. All right. So basically we expect some collision. All right. Now, if I increase the hash table size, then you see that in the new term document matrix, there is no collision taking place. All right. So if you have a hash table of sufficient size, then chances of collision taking place are really, really small. All right. So 2 to the power 20 gives us a pretty good size, which minimizes the chances for collisions. All right. And that is the representation that you can use sometimes if you are interested in using hashing as a way of representing your documents. Sometimes the hashing vector has it has another parameter which is known as the norm parameter. And what you can do is you can use this norm parameter to convert every resulting vector to a size of unit length. What you want to do is you want to normalize vectors so that their length is unit. All right. The same thing is done with the TDF IDF vectorizer. It is done automatically there. That is the resulting weights for any document. If you square them up and add and take the square root, the result will be 1 because that is the length of that vector. All right. Since in hashing, the numbers you are getting are -1 or something else. All right. So basically, the hash table without normalization is not going to give you vectors of unit length. But if you make use of norm parameter, then sklearn will automatically convert these entries or normalize these entries to give you vectors of length 1. So for example, if you look at the first row corresponding to 0, the entries are 0, 0, 0, 0, 0, 0, and then 0.33 with a negative sign, another entry with 0.33 with a negative sign, another entry with a 0.33 negative sign. All right. So if you take each term here, square it up, add them up, take the square root, the result should be 1. You can verify this very quickly that it will give you a unit length vector. So typically, whether you are doing TF-IDF vectorization or hashing vectorization, you should be looking for resulting vector representations where the vectors are of length 1. And if the vectors are length 1, when you take the dot product or do the cosine similarity, automatically the result is normalized and you get a number between the range of 0 to 1. All right. So I think basically you can, go and take a look at this particular blog post, read about it. It gives you all the details of how to implement and get vector representation for your document. All right. So we will stop here.